This video is going to be about orbital diagrams, the last way that we will use quantum mechanics to model an atom. So far we've talked about long and short electron configurations, and orbital diagrams actually build upon a long electron configuration. So let's take a look at an element like number 8, oxygen, where its long electron configuration is 1s2, 2s2, 2p4. We have 8 electrons represented here. 2 and 2 more is 4, 4 and 4 more is 8. Those are the 8 electrons of oxygen, which is element number 8. All right, so what we see here is the energy level expressed with that number that comes in front, then the sublevel that's described with the letter, and the number of electrons that's within that sublevel. What we do not see is how the electrons are spinning, because we know electrons within an orbital have opposite directions of spin, but what happens when you have a partially filled sublevel like we have here? And how are the electrons oriented within the different orbitals of a sublevel? So there's some missing detail here in this electron configuration. And we can clear that up with an orbital diagram, which is a diagram that works vertically. Now, I've seen some people write it horizontally, but I've always seen it done or learned it myself as being done vertically. So if we increase energy going up the diagram, we're going to start at the bottom with 1s. Now remember that orbitals can get pretty complex to draw, so rather than draw them, we're going to diagram them, and we're going to diagram them with a blank line. So no matter what the orbital designation, no matter what shape it has, we're just going to use a blank line to represent an orbital. And remember that the electrons are spinning magnetic charges, or spinning electric charges producing a magnetic field, and they spin in opposite directions producing opposite magnetic fields. So we actually represent the electrons as half arrows. So I'm going to put an arrow there with half of a pointer on it. Now you might say, what's the deal with the half arrow? Half arrow pointing up, half arrow pointing down for a pair of electrons occupying the 1s position. Well, it turns out that particle physicists use half values when they represent electron spin. So we're going to use half arrows to be consistent with what particle physicists would do. All right, so what comes after 1s with 2 electrons? Well, according to this, 2s fills in with 2 electrons. And then 2p is going to fill in. Now remember that a p sublevel is actually made of 3 different orbitals. Now they have these dumbbell shapes to them, so there's 1 orbital, 2 orbitals, 3 orbitals. So what happens when we fill it up 4 times? Well, in fact, the 3 orbitals should be equal energy, so we're going to draw them all in the same level here going up this diagram. And we know from experiment that when electrons fill in orbitals of equal energy, they fill them in one at a time, so they don't double up unless they have to, and they fill them in the same direction of spin. So the pattern that we're going to use is going from left to right, up, 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 and then continue on until we run out of electrons to put in there. So we have 4 electrons, so we have to put 1 down electron in there. So this is the orbital diagram for oxygen. So we have 1s with a single orbital, 2 electrons, 2s, single orbital, 2 electrons, 2p has 3 different orbitals, and we have 2, 3, 4 electrons. And notice that the spin of the electrons is up, 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 and then down. And that's according to experiment that we know that. All right, so if we were going to do an orbital diagram for something a little bit bigger, let's say that we do it for element number, let's do element number 14, which is silicon. The electron configuration is our starting point, so 1s2, 2s2, 2p6, 3s2, 3p2. That's 2, 4, 10, 12, 14 electrons. And again, we can use the diagonal rule to follow that pattern. 1s2, 2s2, 2p6, 3s2, 3p2, not 3p6, 6 is too many electrons. Or we could use the periodic table. 1s fills in the outermost position on hydrogen and helium, and 1s2. So then 2s2 fills in the outermost electrons for lithium and beryllium, so the third and fourth electrons. And then 2p, 1, 2, 3, 4, 5, 6 fills in all these electrons. 3s2 fills in electrons there, the outermost electrons of those atoms. And then 3p2. All right, so what we're going to do is expand our understanding of how the electrons are situated around that nucleus, increasing energy as we move up the diagram. 1s fills in with 1, 2 electrons, then 2s, 1 orbital, 2 electrons, 2p, 3 orbitals, equal energy. Remember, they're equidistant from the nucleus there, so equal energy. Fills up in this order, up, 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 down, down, down. Now, if you fill it up completely, I can't tell what order you'd follow, but when you have a partially filled sublevel like 3p2, it'll become clear then. So after 3s, up, down electrons, and it's kind of weird, but we use arrows to represent, or half arrows to represent these electrons. Then 3p, it's going to have 3 orbitals. Now, no matter what, if there's a p sublevel, you have to have 3 orbitals, even if you showed some of those as empty. 2 electrons are going to occupy these orbitals, so we're going to go up, up, and leave that blank. And you might say, why are we showing that orbital if it's blank? Well, it turns out that when you have 2 electrons in the p sublevel, let's say we call this the 3p sublevel up here in this diagram, the 2 electrons would be filling up this entire sublevel space, like we would take the peanuts, crush them down to make peanut butter, and fill up that entire space 2/6 of the way full. It would be like taking a crayon and shading in that space, but shading it in only 2/6 of the total darkness with which you could shade it. The electrons are actually superpositioning themselves. That's a new term that we use here. Superpositioning means they're in all those positions at the same time, occupying it 2/6 of the way full. Because if it was full completely, like we see down here, there would be 6 electrons there, and we only have 2. So it's important that we show that. Essentially what we have here now is kind of a snapshot in a moment of time where we've frozen the electrons in one particular spot. And in fact, it turns out that if we were to shoot a beam of energy into the atom, a very high frequency beam so that the waves were really tightly packed together, or if we were to shoot a beam of electrons in there too with a scanning tunneling electron microscope, when the energy of a light wave, an electromagnetic wave, or when a beam of electrons hit that, and that would also be traveling with wave-particle duality, the electrons would collapse down into single point particles, and they would appear to be in a particular position. And it's one of the bizarre things of quantum mechanics that we truly don't understand completely, that electrons can do that, where they can kind of behave like waves and spread out throughout the space, and also collapse down and become like particles found in only one particular point for this electron and another particular point for that electron. And that's how particles would behave. They're wave particles, and it's somewhat of a mystery to us as to exactly what that means for our world, that they're behaving like that. So this is how you do orbital diagrams. If you have a D sublevel or an F sublevel, remember that the pictures for D and F sublevels are really too complex to draw, but we can take a look at the diagonal rule and figure out how many orbitals we should have. Remember, 2 electrons per orbital, so if we have 10 electrons in a D sublevel, that means there must be 5 D orbitals. So if you were to diagram a D sublevel, you'd see, let's say we diagram the 4D sublevel, right? We'll just pick energy level 4 there, D sublevel. We'd have to have 1, 2, 3, 4, 5 orbitals represented. And if we had, say, the 4F sublevel, because the F sublevel can hold a maximum of 14 electrons, that means that there must be 7 different orbitals that can be filled up with electrons. Now, if we fill these up, let's say we fill it up completely with 10 electrons, we would see up, 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 down, 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 down. That's 2, 4, 6, 8, 10 electrons. So that would be 4d10. If we have 4f, we could fit a maximum of 14 electrons if we completely fill it up. But let's say we want to fill it up with only 3 electrons. What would we do? We would draw all 7 of the orbitals and just put 3 electrons in there. 1, 2, 3. So let's do one more orbital diagram. Let's do it for a pretty big element, and let's take a look at what that looks like. So let's say we have something like element number 51, antimony, Sb. Now remember, that's electron configuration of 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p3. All right, so that's 51 electrons represented there. Let's do our orbital diagram here. 1s, 1 orbital, 2 electrons. 2s, 1 orbital, 2 electrons. 2p, 3 orbitals. Up, 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 down, 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 6 electrons. 3s, 1 orbital, 2 electrons. 3p, 3 orbitals, 6 electrons. They fill in this order: up, 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 down, down, down. 4s, 2 electrons. 3d, like any d sublevel that holds a maximum of 10 electrons, it must have 5 orbitals. Fill those up: up, 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 down, 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 down. All right, so we have 10 electrons there. After 3d, 4p, 1, 2, 3 orbitals, 1, 2, 3, 4, 5, 6 electrons. Now, I'm running out of space, so what I'm going to do, and you got to be careful if you have a different instructor that they allow you to do this, I'm just going to continue on my journey down here and continue up. So what comes after 4p? 5s, 2 electrons, 4d. You know, if you have a college professor and they don't want you using an arrow like this, I'm not sure what they'd have you do. Maybe redraw it so it all fits. So after 5s, 4d with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 half arrows, each half arrow representing an electron. If it's pointing up, the electron is said to be spinning up. If it's pointing down, the electron is spinning down. And finally, 5p should have 3 orbitals with 1, 2, 3 electrons. So we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 2, 4, 6, 8, 30, 2, 4, 6, 8, 40, 2, 4, 6, 8, 49, 50, 51. So this is the orbital diagram of element number 51, antimony. Now, you might say, that is a lot of writing, and I agree. Now, there really is no shortcut for an orbital diagram that's internationally accepted, but in my class, I might sometimes ask you with a big element like this to just diagram the very last sublevel. Because really it's that last sublevel where you can see the details of, do you really know the order in which the electrons are filling in? So the last sublevel is always that very last piece of an electron configuration. And to finish this up, I just want to point out that you can actually look at a periodic table. Let's make sure we're focused here on antimony. And you can see that antimony has its last sublevel filling in right here, and that's 2p, 3p, 4p, 5p, 1, 2, 3. So 5p3 would be the last sublevel. If I ask you to just diagram the last sublevel, all you'd have to do is show me this very last part of it. If I ask you to draw the entire orbital diagram, then you have to start at 1s and continue on till you get to the end. Hopefully that clears things up. That's it for quantum mechanics.